Hello everyone. Thanks for coming. I actually was here not that long ago. I can't remember if it was last year or early this year, and there's far fewer people, but I think it was like bad timing. So I'm going to talk about Argonne National Laboratory, specifically engineering at Argonne, and so I'll give you a little background on me. I'm going to talk about Argonne. I'm going to talk about where I work, which is the Advanced Photon Source, which was on the picture previously during the preliminaries of the meeting. There's that picture of that particle accelerator, and that's the Advanced Photon Source. I'm going to talk about engineering at APS. I mean, there's a lot of engineering done in Argonne, but I'm going to kind of talk about what I do and what other engineers do at APS. I'm going to kind of give you my opinion on things that are important as young engineers as you go through your career. What things are important, what you like. This is based on, let's say, mostly based on my own experience, and not necessarily. Some of this might be, oh, I wish I would have done that, so I'm going to tell you to do it. Then I'll talk about some opportunities, and along those lines, this is a kind of perfect time to check. So I know there's on the posters I saw. That I will collect resumes. I'm not going to collect resumes. Because quite honestly, giving a stack of resumes to somebody at Argonne, they're just going to take it and, okay, I'll get to that at some point. It's not like there's somebody waiting there. Gosh, if we only had some resumes. And in fact, Argonne doesn't even accept, I just learned this recently when I was kind of preparing for this, they don't even take paper resumes anymore. So I'm going to talk about this, but what you can do is go to the website, go to the career website, look at that, and you can create a profile and apply for jobs, and kind of see what's going on. So I just want to give you a little background on myself. And sometimes I think I'm a hands-on guy. I've always wanted to be an engineer. So it's maybe in sometimes when I'm hepped up on caffeine or something, I might think of myself as this guy. I think probably most of you probably know who this is, Thomas Alva Edison, who's a very hands-on guy. But the reality is, maybe the people I work with think of me more like this guy, Professor Frank, kind of a bumbling fool. But the reality of it is, so I'm a mechanical engineer. I work at the APS, which is, I think that's probably the exact same picture. And what I do there is I support science. I'm kind of in a supporting role. Because what the APS is, it's a user facility that is built and operated by the government. It's your tax dollars at work, basically. And what I do there is I design X-ray instrumentation. And in doing that, I do a lot of different types of analysis for various types of devices. And I'm kind of it's a fairly my kind of portfolio of work is fairly diverse. And what I really like to do is I like to do R&D, but kind of getting back to this, I'm in a support role. Everything that I do, kind of the investigative things, has to kind of tie into some sort of application. It's not like I can say, oh gosh, I want to find out, if I can make this positioning system go faster. That may be cool, like that I want to find it out, but I have to tie that into some application. So just a little aside, the stuff that was talked about by your officers at the beginning, that old guard competition, I highly encourage you to take advantage of things like that. Because somebody said, I don't remember her name, but she said, one of the officers said that, engineers, we get faulted for not being able to communicate. And I'll extend that to say, well, there's a lot of people, engineers, or whoever, that cannot communicate. And communication is really, really key. Because you can have a great idea, but if you can't communicate that idea to somebody and sell that idea to somebody, you might as well not have the idea. So, it's about that, it's kind of, the end result is the same. And being able to communicate will also enhance your career, because you'll be able to communicate what you want to do and why you want to do it, and then perhaps be able to do what you want to do as opposed to do what somebody else wants to do. So things like that, getting up and becoming comfortable with doing this, standing up in front of a group of people, is a very, very, very useful thing, because all the engineers that I know, at some point or another, they have to do this. So that's a really, you should really consider that. So just continuing a little bit of background about myself. So I'd already mentioned, I wanted to be an engineer for pretty much as long as I can remember. And I was always involved in some sort of, like as a kid, some sort of experiential thing, like a summer program or whatever. And I went to UIC. Like, this is a very familiar place for me. I defended my PhD in that room next door. I sat and fell asleep in those classrooms over there. Though I wish, like, looking back, this is another hindsight is 2020. It's like, I wish I could go back and like spend some time in my undergrad classes, like, and really put my all into it, as opposed to sometimes just getting by. But so I spent a lot of time here, and I knew, I wanted to be a mechanical engineer. I participated, I did some undergrad research, which was really good. I didn't do any internships, well, until I said I did an internship. That was kind of in between undergrad and grad school. And I kind of, doing this internship and doing the undergrad research, I kind of realized that I like, one of the things I love to do is figuring stuff out. Like particularly, like for example, figuring out, let's say, why something doesn't work. And then, kind of after I did this, the master's, I did my PhD. It kind of just, I don't know, it seemed like the thing to do. Like it wasn't, it's like a door open and I kind of walked through it. I didn't have necessarily a very, when I started out as an undergrad, I didn't have an agenda that this is where I was going to go. And I'll talk about later on, like how you might explore what it is you want to do. But the PhD is how I ended up out at Argonne. So I started out there as a student, and then I ended up out at Argonne. I stayed there.
Doctor, I have a question.
You guys say Kurt.
Kurt, you say you got a PhD here?
Yes.
Who did you do research with?
Dr. Tom Royston, who's now the head of the bio department.
And what was the thesis?
It was on modeling, I don't remember the exact title, it was on modeling harmonic drive gearboxes, which is a type of mechanism for motion reduction. It's one of the most common applications is like arm-type robots. I'm sure if you go upstairs, probably sitting up there someplace where you can look it up on ProQuest if you're super interested.
Thank you.
Email me. But yeah, so I kind of just, like I said, I didn't have a real directed, I didn't have some path that I knew exactly that's where I wanted to go. I just kind of saw, as I went through, I saw interesting opportunities and I kind of took them. And it ended up working out okay. I think it worked out pretty well. I like what I do, but hindsight gives you a lot of, it's like, wow, if I would have known this. And that's actually one of the things that's one of the reasons why I'd like to come here and do this, to maybe give you a few, plant a few seeds, or give you a few tidbits of information about what may be important, or things that you should be on the lookout for. So, at work, so my title's an engineer, but so if we think about, what is an engineer? And I stole these from Wikipedia there. So engineer, they say, an engineer is a person who applies scientific knowledge, mathematics, and engineering to develop solutions for technical problems. And the scientist is somebody who engages in systematic activity to acquire knowledge or discover principles. And okay, maybe this is what I did this time. So what? Where I was going with that is, engineer, like the kind of, I think, common way of thinking is that engineers design and scientists stuff. But what I found is, Argonne's a pretty cool place, and where I work is a pretty, I think, like I said, what I work on is pretty heard. And I like to think that my job is kind of a mix. And so I do some engineering R&D and applied science, and I do some studying to design. So that's, it's a neat, I think it's a neat mix. So that's about me. So what is Argonne? You guys already heard that it's the first national laboratory, and that's exactly right. The national lab system did not exist until Argonne existed. It's a direct descendant of Enrico Fermi's MetLab, which is what the so-called Manhattan Project came out of. So these are two images up there on the left. That's Enrico Fermi. On the right is a artist's rendering of the first self-sustaining nuclear chain reaction. That happened just kind of southeast of here at under Stagg Field at the University of Chicago. And what we see there is basically a pile of like the bricks. Those are actually graphite bricks. And the guy in the bottom is like pulling out the final control rod, and the thing's going to go critical. But Argonne grew out of this, and like the original mission was kind of nuclear power and research in that area. Since then, it's become like a very, it's way more diverse than that. Certainly, nuclear power since probably like 3 Mile Island in the States is not a very popular thing. Argonne still does research in that, but it's just kind of one part of the mix. So we do, there's national security stuff, there's a lot of biological stuff, there's kind of the broad moniker of energy security, people looking at like, well, how can we make vehicles more energy efficient? So we have to rely on oil less, things like that. And then there's, this is kind of one of our stock slides, but we kind of like to think of ourselves as doing kind of transformational science, things that are really going to change how, at least some part of the world works. And a big part of that is our user facilities. Yes?
Can you give an example of what you guys do for national security?
Yeah, okay, so Argonne is a place of about 2,500 or 3,000 people. So, I work in my little box. And so the only reason why I'm saying that is to say I'm not an expert in this, but they'll do things like this image back here was that thing up there. You can see that's Chicago, and there's some red cloud of death coming in. And I think people do simulations on looking at for a very simplistic thing. Well, like let's say there was some sort of aerosol that was dispersed. How is that gonna move about? I mean, there's other aspects of it. There's a lot of national security stuff that is done. If you go on the website, you can probably find more examples. But I know there's people there that look at the power grid, like modeling the power grid. Let's say somebody takes out some sort of substation or something, or a series of things. How will the grid collapse? There are things like there's some much more direct national security implication or applications. Like they look at, so they're one of the. And I'll talk about Argonne is part of the DOE. DOE is responsible for stockpile stewardship of nuclear weapons. And there's some. This isn't a very large, it's a very minuscule part of what Argonne does, but at the Advanced Photon Source, some people are using the X-ray beams to look at the behavior, very, very small amounts of fissile material, so they can better, so they can take that information and feed it back into computer simulations of nuclear weapons. So it's like there's things. I mean, there's a lot of stuff. So a big part of Argonne are these user facilities, which I like to call kind of like fitness centers for scientists. Or engineers for that matter. It's like, you can go to a fitness center, and you can use a treadmill, you can use an elliptical, you can, use all sorts of weights, and you don't have to own them yourself. It doesn't have to take up space. Maybe it's, a very specialized piece of equipment. These user facilities that you see up here, of which the Advanced Photon Source is one, they're typically things that cost a heck of a lot of money to build. And the only people that are going to, the only organizations that are going to be able to build this are government organizations. You know, it's kind of out of the reach of the scale that these things are, is out of the reach of universities or in private industry isn't going to want to do it just because it's not going to turn a profit in, you know, 3 or 4 years. So these facilities, people come in, they're actually for free. You apply for, you know, it's a competitive process. You fill out some application. This is what I want to do. This is what I want to use the Argonne Leadership Computing Facility for. I've got this really hard, let's say, multi-body dynamics problem. I really need some big computing power. It would really make a huge difference, and you can use, you know, you can use that computer. Or you've got some material problem, you can use the X-rays at the advanced photon source to do it. And so this is, you know, these are our user facilities. So I want to talk a little bit about, well, why is Argonne important? And it's a very, you know, I've used this word diverse a number of times, but there's a lot of different types of science that are done there. And you know, just to kind of cherry pick, back in 2012, these two guys won a Nobel Prize in chemistry. And there's in the quotes, there's what the actual title is. It's for studies of G protein coupled receptors. And I'm an engineer, so I really don't know that much about this stuff, but this is a protein that is in the wall of a cell. And it allows the cell to get signals from the outside to the inside of the cell. It's basically, it's a huge, it's one of the most important mechanisms in our body, how things work. And these guys, you know, were able to basically study this, figure out the structure. And you can see that half of all pharmaceuticals target these proteins. So it's like, to gain understanding of this is very, very important. And they did work at APS. And they did work at a beamline at which I worked. I mean, it's not like I, you know, took their hand or anything, but I like to think, you know, I was a little cog in this big machine that helped this discovery. This is actually, since I've worked at Argonne, this is the 3rd Nobel Prize related to work done at Argonne. So there was actually a 2009 Nobel Prize in chemistry. It was also given to a group of scientists that used the APS to do their work. This is a little more, let's say, day-to-day relevant application. So Argonne developed the battery technology that is in the vault. This technology was then licensed to a company that you know, produces the batteries. Another sort of important thing is this, we have this, what's called the JCESR, Joint Center for Energy Storage Research. And it's a pretty ambitious, it's kind of like, it's been likened to like a moon launch, but for energy storage. You can see up there it says goal 555. That means store 5 times, they want to develop a battery system that can store 5 times the energy, cost 5 times less, and they want to do it in 5 years, which to me sounds pretty incredible. So we're part of this. There's a lot of people that do work on this. I mean, I don't really have anything to do with this. I just wanted to, I mean, other than the fact that people who do this work use the advanced photon source. You know, so this is another kind of example of what Argonne does. We have a lot of educational programs. We have stuff for undergraduates. We actually go all the way down to like, some middle school stuff. There's a lot of really, really great opportunities for undergrads. I know some of you are probably close to graduating, you're more interested in career stuff, but some of you are perhaps earlier on in your schooling, and I mentioned internships. This is I think I did. This is a great place, you know, to see about doing an internship, and I'll kind of talk a little bit. I'll talk more about that towards the end of my presentation. So I've talked about myself, talked about Argonne, and so now I'm going to give you a little bit of background as an advanced photon source, because it's an unusual place. So if I just launched into, like, oh, this is what I do, it's like, it's better if I provide some context. So basically, the advanced photon source is a big X-ray machine. I think we're a little bit more adept than these guys, but it is pretty darn big. You can see, so it's 351 meters across. That's a circumference that the beam travels, or that's the circumference of the ring in which the beam travels. Or sorry, the diameter of the ring in which the beam travels. The circumference ends up being about 1 kilometer, the beam path, which means So I'm in that, you see where it says Central Lab Office Building. My office is in there. Today, I was actually working kind of down below where the label, where it says 351 meters. And if you forget something, which I did, it's a long way to walk back and forth. So it's a big place. I certainly get my walking in. And you can see kind of the rest of Argonne, and actually that direction is east. If the camera was facing that way, you'd actually be able to see downtown. So the APS is what's called a storage ring synchrotron. The synchrotron is just a term used to describe synchrotron. It comes from this synchrotron radiation, which describes if you take electrons and you move them, they're charged particles, and if you move them, if you accelerate them through, if you curve them, so you're accelerating them in a magnetic field, they emit photons. And this machine is designed such that those photons are in the X-ray range. And really the only reason why the APS exists is because of engineers. There's a whole really amazing bunch of people that conceptualize, well they didn't conceptualize it, but they take the kind of the physics end of things. There were physicists who kind of conceptualized this idea, but it's the engineering that really translates, obviously the physics is very important, but the engineering is really what translates that into a usable thing. So here's just a simple cartoon of how the APS works. So there's basically, we produce a bunch of electrons. There's what's called basically a cathode gun, where some electrons are boiled off this electrode, and they are then accelerated, and they go through a series of accelerators, and they're brought up to an energy or speed. It's 99.9999999% the speed of light. So these are what would be called relativistic electrons. They travel, the blue arrow there is kind of the path that they travel. You pass these electrons through a specific magnet structure, represented by the horseshoe magnet there. They will produce these photons, which is X-ray light. We take the X-ray light, and we have some optics represented by that magnifying glass, and we'll focus them, and maybe we'll shine them on proteins, and then we can figure out, the scientists, the users can figure out, well, what does this proton look like? They can do things like look at the structure of metals. You can take like a piece of, let's say more engineering application. You can take a coupon of some material, put it in a tester, kind of like your typical tensile tester. You could look at that while under load with the X-rays and actually see what is going on with the actual structure of the material. And those are just kind of a couple examples of what you can do with it.
Kurt?
Yes.
This is a question.
So, do you need that large of a facility just to emit X-rays? Or could you talk about the advantage of this type of imaging versus just like standard X-ray imaging?
Okay, so the X-rays have it's a good question. These X-rays, kind of go up to this slide here. The X-rays have very, very unique properties. So they're very intense. Most of you here have probably had a medical X-ray, and that uses an X-ray generator. I think typically it's like some sort of little short electron accelerator where it takes these electrons and slams them into a tungsten target, and or it actually slams them in. Depending on the wavelength of X-rays, the target might be copper or something. I'm not really that tuned to those types of X-ray generators. But what happens is those X-rays are emitted in kind of a spherical direct. Like they kind of go out. The intensity is the same. It's like you have this high divergence. They just go everywhere in kind of a sphere. So you might be putting a lot of power in there, but really, you're throwing most of that away. Because when you make a medical X-ray, there's some beamline where the X-rays come down, and there's a bunch of collimators. So you get a beam of X-rays, let's say that shines on your cheek that's been collimated with some tungsten collimators, and a lot of the x-rays are thrown away. The other thing about those x-rays is they are not all, like, they have kind of a broad energy range. They're not, you can think of, when I say energy, that's directly analogous to like color.
Yeah.
So they have a very broad energy range, and they're not coherent, meaning all the wavefronts are not moving coherently. So when you use a synchrotron to produce X-rays, you can get X-rays that are extremely intense. So the amount of power in our X-ray beam is can be on the order of, let's say, 24 kilowatts in a, let's say, let's say a 2 by 2 millimeter area. So it's a huge, very huge power density. And then we can take those X-rays and we can very finely select the wavelengths. We can do very specific, that's very useful for experiments. Then what we're seeing here is these white lines. Each one of these white lines represents an X-ray beam line. We have 70 X-ray beam lines. We actually have more than that. The facility was originally designed to have 70. People have come up with clever ways of actually doubling, kind of making double use of some of the beam lines. So now we can serve a huge number of people. We serve like 10,000 individual users every year. So, just recapping how this works. So it's like we take these electrons, they're emitted from a cathode. Basically, the simplest way of doing that is you have a cathode that you heat. It's a metal. I don't know what metal it is, but they heat it, and the electrons kind of boil off. It's in a vacuum, and heat that up to like 1100 C. You get this effect. It's very much like a vacuum tube or something. We accelerate in this. We're at point number 2. There's what's called a LINAC, which stands for linear accelerator. We do a significant amount of acceleration, so it's up to 99.999% the speed of light. They're injected into what's called a booster synchrotron, which is that where it says number 3, which accelerates them up to the full energy. And then they're injected into the storage ring. You can see there's the circumference, so it's about 1 kilometer. So now they're traveling around the storage ring. Yes?
How do you gain that much speed for the electron?
So there's a couple different accelerating. The LINAC has basically these RF cavities. It's like this repeating RF cavity structure that kind of gives the electrons a kick of, they're oscillators basically, and they give the electrons basically a kick every time they pass through one of these accelerating cavities. And then when they go into the booster synchrotron, the same thing happens, but it's a different, they do it at a different frequency, but so there are these RF cavities, which is nothing more than kind of like an antenna, and they impart the energy to the, to increase the speed of the electrons. So once the electrons are circulating, I said, well, we pass them to these magnet structures and they produce the X-rays. And there's 2 ways we can produce the X-rays. There's what's called bending magnet radiation, which comes out of this long thing is just a dipole magnet, and as the electrons pass through, if you think to your physics, and electrons pass through just a dipole field, they're going to experience a force which is going to cause their path to curve. When they curve, there's a fan of light emitted. There's another way, a more advanced, or not, let's say, probably more popular way of producing X-rays is called an insertion device. And the point of this slide, I know it's kind of hard to read, but these are all, there's like a very, each of those little colored blocks is a different type of magnet. So probably the most popular way or the most useful way of producing the X-rays is using one of these insertion devices. And they're called insertion devices because they are inserted into a straight section in the storage room. And what these are, there's a permanent magnet array. You can see these 2 jaws. They have these, you can see south, north, south, north, south, north, south, north. Things about 3 meters long. These jaws can open and close. And as the electrons pass through these jaws, they kind of wiggle. There's and by doing that, if you select the magnetic period a certain way, you have all of the radiation, all the X-rays are produced in a very narrow cone. And that's kind of what you see, that gray blob that's coming out. It's a very narrow cone, and it is laser-like. It is not a laser, it's not completely coherent like a laser, but it's laser-like, and that allows you to do certain things with the X-ray. So this is one of the main reasons why we don't use, you can't do these things with a, you can't do the same types of experiments with, let's say, what we call like a laboratory X-ray source. I mean, you can do some of the experiments, but you can do them better at a synchrotron. So this is a view actually inside the storage room. So we're standing, this is kind of taken with like some fisheye lens, that's why it's distorted. That black thing there is an undulator. That was what I was showing you on the, or an insertion device. That's why I was showing you on the slide. If you look to the right, these magnets kind of go off and they just curve around. If you're actually standing there, it just kind of goes off to the distance. The blue magnets are focusing magnets. The yellow magnets are another type of focusing magnet. The big red magnet is one of these bending magnets, and that's actually what causes the electrons to make the circle. So the electrons travel in a vacuum chamber. And one of the interesting things is this, it has to be very, very clean, because if there's anything in there, the electron's going to slam into whatever's floating around in there. So if you think back to, let's say, chemistry or physics, you may have heard the term mean free path. The mean free path of a particle in that tube is about 1,000, it's thousands of kilometers. The mean free path of a particle in this air here is about 63 nanometers. So every, any particle, any gas molecule here is only moving 63 nanometers before it slams into another one. And we think of this as, empty space, but that's a heck of a lot more empty. So looking the other way, it's kind of, you see, it just kind of goes off. A lot of complex stuff here, a lot of engineering going into this. So to drive home the point, it's really, really clean in there. It's more akin to not Navy Pier on a Saturday, but kind of Death Valley in the middle of nowhere, but kind of rock sliding across the playa. So there's a lot of engineering challenges actually to make something that clean. You have to have very good surface quality. You have to handle it a certain way, because like one thumbprint, if you just put your thumbprint on there, contains some very, very large that oil in your skin oils. When you evacuate that chamber, that oil all kind of evaporates, and now it's floating around in there, so you can't touch that stuff at all, like with your bare hands at all. You have to use very specific handling procedures. So the X-rays are produced, and they come down an X-ray beamline. And so this wall, this gray thing here with the zigzag, that is the wall that delineates, like on this side is a particle accelerator, on this side are the X-ray beamlines. And there's a port which the X-rays come out. All these blobs here are different like conditioning devices. They're mirrors, different types of optics, shutters to shut the X-rays off. So we do a lot of conditioning, then there's some transport, and then down at the end there'll be an instrument of some sort. So it's just kind of like a generic beamline. So I just wanted to kind of briefly say, like, well, how do you use these X-rays? So to use the medical X-ray analogy, that's like one of the most basic ways of using X-rays. That's you shine X-rays on you. The X-rays, some of the X-rays are absorbed. Like, some parts of you absorb X-rays more than other parts. There's an image made. It used to be film. Now it's a CCD. That you have an image based on what's called absorption contrast. So that's a type of imaging. So we can do imaging. There's different ways of doing imaging. There's also, you can do what's called scattering, where X-rays, because we have these very intense beams, materials that have, a lot of materials have some regular atomic structure. And you could exploit that structure to learn about the material. You could shine the X-rays on the structure. And the X-rays, the photons will actually be scattered by the atomic structure. And you can measure that scattering pattern and determine something about the structure. You can also do spectroscopy, where there's, you can use the X-rays to basically will excite the atoms, or excite the electrons in the atoms of whatever material you're shining them on, and then when the electrons return to their ground state, they'll emit photons. And those photons will be characteristic of the material, so you can tell something about the material. So it's like, you can use all these different, this is, that schematic there shows the basic idea of how it works. It's like, once again, there's electrons circulating, we produce X-rays. There's some sort of optic to condition the X-rays, maybe focus it, maybe select the wavelength. We shine those on a sample, and then we detect the X-rays that either pass through or are scattered from the sample. So we can do all those techniques, and you can also do those techniques looking at things in real time. There's a big push to look at things as they develop. Let's say look at a cathode on some battery, or some part of a fuel cell while it's actually operating, to determine what's going on. Because X-rays are highly penetrating. You can do things with X-rays that you can't do with any other method. So kind of the types of techniques that are used. And a lot of different people use this. This was just a generic slide that I grabbed from our Argonne communications people. And UIC is actually out there. UIC uses the APS. I know they're Carmen Lilly is a APS user, but you can see there's a lot of big names there. So it's a pretty useful thing, I mean, both from the private industry and academic. There's a lot of people there. So now I'm going to talk about a bit about the engineering. So I'm going to talk about some things that I do, some things that other engineers have done. But what I like to think, how I work as an engineer. I've got a toolbox for some design, do some analysis. Sometimes I have to actually measure things, and then there's that. Actually, kind of changed the slide up recently. There's a report, and that gets back to that, like what I was talking about, the old guard thing. At some point, you need to communicate what it is you did, because as my boss has told me a number of times, if it is not written down, it did not happen. And that's true. I see that in my own existence, just in simple things like, man, I asked Joe what the requirements were for this thing, but I didn't write it down, so now I gotta go ask Joe again. So there's like simple things like that. There's also just when I do something, to make certain that that information can be used later, it's like reporting or presenting or whatever, communicating that in some way. I probably should say communicating is extremely important, because I think as engineers, a lot of people think, well, engineering is the three things over here. And they kind of forget about that, or they don't think that I'm going to do my work, and then when I'm done with my work, I'll tell somebody about it. But actually, communicating is really part of your work. So if you start to think about communicating and writing as being part of what you do, it's like, maybe the fun stuff is running an experiment, but writing and communicating is part of your work. It's not a separate thing. So start to think about that as part of what you do. I think is really, it can kind of, it makes it less of a problem to do. So this is something, a project that I've worked on recently. There's no such thing as good vibrations around the synchrotron. What you see in the upper left there is it's a vacuum tank. The side has been removed, and inside it you can see there's some stacks. This and this are motion. They're stages that provide certain motions, and up here are silicon crystals that the X-rays hit, and by moving these stages, the scientists can select, this is called a monochromator, they can select the wavelength or energy of the X-rays. And this particular device was vibrating quite a bit, it did a lot of beam motion. And if I had a laser pointer here, I could show you. I think a lot of you probably stood with the laser pointer, and if you point at something far away, particularly if you had a cup of coffee or something, points jumping all around, and it's kind of a similar deal here. The X-rays are coming off this optic, but the experiment is, say, 10 meters away. So if this optic moves a little bit, you're going to have significant beam motion. So just to kind of show you what level of vibration are we talking about? Well, this is a plot of our floor vibration. See, so it's the red, blue, and green. These curves here are the X, Y, and Z motion. This line here, right there, is 1 nanometer. So we're talking small vibrations. This line here is 10 nanometers. So if you take, that might be very small vibration. I mean, if we measured the floor here, if I had to guess, there's actually, I think, a basement here, we're not on grade. It would probably be, more like high tens of nanometers, depending on what's going on. If people are walking down the hallway and stuff, they're probably hundreds of nanometers. You go upstairs, it's going to be, definitely hundreds of nanometers, depending on, maybe even up to a micron. But we're a very quiet facility. This is like pretty low level vibration. However, it gets amplified through those stacks of states. And I was called in, because my background is actually vibrations and dynamics, and I was called in to basically fix this. And, so what did I do? I had to kind of figure out why is this thing vibrating? So I looked at the design. It was a design that somebody else had done, and what I was able to figure out is the bottommost component was just way too flexible. And this is kind of an interesting, this chart here shows so this is force on this axis and this is deflection. So what these curves are showing is basically if you take the slope of this, it's stiffness, so it's a force deflection curve for various types of bearings. Because those stages move, and to make them move, there's some sort of bearing that allows that to happen. Well, there's a lot of different choices in bearings. And a common, if you've ever worked on your bicycle bearings in the hub of your bike are, they're spheres. And they are spheres on let's see, spheres, okay. Yeah, they're sphere on internal cylinders. And that actually is a pretty stiff bearing. There's other bearings you can have where there's just a sphere on a flat or something like that. And that's these curves down here. The most stiff kind of rolling bearing is basically a cylinder on a flat surface, because now you have a line contact, not a point contact, so you get much less deflection. That's what this, you can see the slope of this is much higher, it's much stiffer. So I was able to kind of do some, this was just, you probably heard the term Hertzian contact. This was just some simple, pencil paper calculations, went into MATLAB, plot this stuff out just to give me some comparison, say, oh, well, wow, the way this thing is constructed is actually not very stiff. So that was kind of like just a good, that was one of the pieces of information I used to kind of solve this problem. In the end, I was able to definitively determine that the stage, which component was problematic, and we sourced a replacement, which actually the vendor kind of messed that up, but because they did not actually listen to this. It's like we told them what we wanted to do, and they actually ended up not meeting our spec, but so now we're kind of going back and forth with them again to fix it. But so that was just kind of an example of a kind of a problem-solving thing that we did. Now, from the design standpoint, there's you guys have all heard of Picasso. What a number of the Art Institute has Picassos in the collection. One of my collaborators, a scientist that I work with, so you heard me say I support science. Lots of times that involves, there's some scientists who get some idea, and it takes some engineers or an engineer or a team of engineers to make that idea into a practical, usable thing. So this guy on the left, his name is Volker Rose. He was working with a scientist, actually a curation scientist. She's a curation physicist is her title, Francesca Casadio from the Art Institute. And they had this really cool thing where they used one of our instruments to look at, they were able to definitively determine something very interesting about Picasso. You think of Picasso or any like fine art, like, oh, it's like really fancy. Well, it's been suspected for a while that he used house paint. And what these two were able to do, using the instrument on which I was one of the people that helped design it, is they took a minuscule sample of that paint, and then they went on eBay and bought some, this paint says Rippling, it's an old, this is a can, you can see it looks pretty old. They bought some can of house paint from a long time ago, and compared, used the x-rays to determine what the chemical composition was of these two things, using they used basically some very, very small sample, a minuscule sample from the actual art. In fact, I don't think it was from the natural, I think it was from the side. And it wasn't just the chemical composition, but it was actually the structure of the kind of the chemical constituents. And this was revolutionary work because no one had done this. No one had been suspected, but no one was able to actually prove it. But these two were able to do it. It was actually right up in the New York Times. His phone was like ringing nonstop for like days. It was pretty cool. So yeah, Picasso used just common house paint. And what they did is they looked at the nanostructure using this big silver thing there is what's called the nanoprobe. And it's a nano-focusing X-ray microscope. So it takes the X-rays and focuses them down to on the order of like 20 or 30 nanometers. And that's what enabled them to make, this is kind of there's a zinc and iron. This is kind of micrographs of the sample of the paint, and they were basically able to kind of map out the, you can see that the scale bar is 1 micron, so you can see all these structures down here, and all these little small dots, those are nanometer scale structures. So they were able to map out this like kind of where the constituents are in a way that you couldn't do with any other instrument. And this is one of the things that I've been able to work on at APS. I worked on designing the tank. I did some of the stuff, kind of the motion system inside, some of the testing on that. I didn't do the design. I designed the support system for the whole thing. But it's a pretty cool, pretty amazing instrument. Yes? Oh. Okay, so let's, so those are some of the engine, I want to talk about, all right, so, I talked about there's a lot of engineering there, but what I want to kind of pass on is, I think some of the most important stuff is to engage in things like this, going to these meetings, going, seeking out opportunities where you're going to learn something, to push your limits of knowledge and comfort, and learning about things that you didn't know you didn't know. And by having these experiences, you might find out about something that you don't like, which is just as important as finding, sometimes more important than finding out about something that you like. I like this idea of a growth mindset, which is really a belief that your abilities as an engineer are kind of, you can cultivate those, you can improve those. Just because you don't know a certain thing doesn't mean that you can't learn that. And really, if you want to, this isn't necessarily so apparent in undergrad, but as you go into, let's say, an internship, or to a career, or to graduate school, one of the things that I found most helpful is this idea of being comfortable with being uncomfortable, which is basically feeling stupid. Being comfortable with feeling like an idiot. And there's there's actually a journal article that speaks to this. It was in this Journal of Cell Science, and I have the link there. Great, it's like 2.5 pages, very short, but really great. So, just to hit on I can't really emphasize the writing enough, because there's a lot of people I work with, and they cannot communicate what they want to do. And it's it's frustrating to work with people who can't communicate what they want, because it makes it hard for me to decipher what they need. And a really important thing is when you write, writing isn't the end product, it's a process. It helps you organize your ideas. And there's lots of times when I sit down to write something, I will have, it's like oh, okay, yeah, I get it now, I should be doing this. So, you know, there's why, like, participate, seek out these experiences. There's a lot of opportunity just around here. You can do undergraduate research. So there's opportunities for undergrads at Argonne. So this is the link, and I know Ned has my presentation, well, it's actually here. So you guys can distribute this if you want, there's the links.
Who posts on the website?
Yeah, it's posted on the website. There are, that's a link, if you go there, there's a whole host of, you know, now's a good time to look for summer. Like if you want to do a summer internship, start looking now. Some summer internships actually start, the applications close like before the end of the year. So it's definitely a good, you know, it's good to start looking at, and not just Argonne. If you think, you know, if you're like, wow, that national lab idea seems kind of interesting, there are other national labs. You can go peruse these, like, other national labs. You know, if you just Google national labs, you'll come up with them. But most of them have internships. There's obviously also careers. And that's linked to the career website. And I said I wasn't going to collect resumes, because I mean, really, you can go there. You know, like I said, they do not. You can actually see it if you go to. Yeah, if you click on external applicants, there'll be a whole bunch of other links, and one of them is like an explanation. It'll say, we do not accept, you know, no paper resumes. So you have to make a profile. I don't think it takes that long. Then you can put your resume up, and then when you just look at the look at the website every so often, and you can see the job postings. You know, where I'm working, we're not hiring any engineers right now, but we're in the middle. Didn't really talk about it that much or at all, but we're kind of at the beginnings of a huge upgrade, like basically a $450 million project to upgrade the advanced photon source. At some point, we'll be hiring engineers. We had, like, it kind of went like this, because we were working, and then we actually had to lay some people off because of some changes. But you know, this is where you want to go if you're interested in a career. And I will say, like, just, yeah, it's like just, yeah, check it out. It's definitely worth looking into. So thanks. If there's any questions, or if anyone wants to talk to me about it, I kind of didn't hit on so many engineering applications as consumer time. Yeah.
I'm not really sure if you know this, it might be outside of your realm, but do you know how much energy it takes to run this accelerator? Because I imagine as it travels around, it's scavenging all those X-rays as they go down the beams. So you have to probably put a lot
You have to
into
put,
it
so
to
every
keep
time,
going.
so one thing is that every time the beam, you know, it's called a storage ring, which means you put the electrons in there, and we want to keep them there. So as they produce the X-rays, their energy actually decreases, and if you didn't do anything, they would kind of eventually spiral into the center and just hit the wall of the tube. So there's RF cavities that are constantly putting, you know, every turn they could basically give the electrons a little kick. That's one of the power consumers. The other thing is all those magnets dissipate a huge amount of power. They're all normally conducting magnets, so there's the resistance of all the copper windings. I forget what it is, but it's some ridiculous. It's a huge part of Argonne's budget, actually.
That's what I was wondering, is how they power that and where that's coming from.
It just comes from the grid, but we,
Really?
yeah, I mean, it just comes from the grid. I mean, it's not, I don't think it's like, it's a lot of power, but I don't think it's necessarily like, on the scale of things, you know, a big manufacturing plant probably uses the same amount of power. So, yes?
Like you said, the cathode supplies the electrons for the UPS. Is the cathode literally replaceable, or is it replaced every once in a while?
Yeah, I think that's actually not something that I have ever worked with, but I think it is. That is a maintainable. They have to maintain those cathode guns, the sources. Actually, we have redundancy. We actually had a problem with them a few years ago, but yeah, that's a maintenance item. I don't think, I think there's some erosion or ablation or something like that, but I don't know the exact details of that. Yes, over there.
So if you wanted to be a staff engineer at Argonne, would you need a PhD then?
That's a great question. So you don't need a PhD. There's plenty. So the group in which I work is pretty diverse. We've grown a lot since I was in the group. We have, I think we've got about it's actually one of the bigger groups at APS. There's about 40 people, and I think about 20 engineers. And of those 20, only probably about 10, maybe less, 7 have PhDs. A lot of people have masters, and then some people just have bachelors. A lot of, I would say, I bet you the majority of people have at least a master's. But what it does do, like if you, it depends on what you want to do. I mean, you can be, these people, they make good contributions. But what I have found is that in this environment, having a PhD, when we're like, I said we're in a support role, and there's, the scientists kind of run the show. And if you want to be like on an even, like, kind of keel, having a PhD certainly doesn't help. I mean, people with, bachelors with like 20 years of experience are doing, all sorts of really awesome stuff. But it just, I think if you have an advanced degree, and I think this goes anywhere, it will enable you to, kind of maybe have a little more leeway in what you do in your job. I mean, I can only speak from my experience, but it certainly enabled me to kind of carve out a niche. Now, it's not to say you have to get a PhD. I would say these days, getting a master's is probably not unreasonable for anyone, regardless of where you work. It's just at some point, you don't have to do it right after school. But it's just, you learn a lot. It's just a really great, you learn a lot at work too, but it's like school is kind of it's a different sort of thing. Yes?
You said that the electrons were accelerated to 99.9 whatever percent of the speed of light before they were inserted into the ring. Yeah. So where's like the length of space where they actually accelerated?
So so these structures right here, so here's where this cathode gun is. They're accelerated here, and then the final acceleration is done here. And then when they go into this, there's a transport line that takes them from here to here, and then they're at kind of with full energy. Yes?
Will you accept international students for internships?
Yes. Yeah, once again, it's like a little bit more. I mean, there's no real, like, we don't do a lot of national security work, but paperwork tends to be more, being a government institution, we're kind of heavy on the paperwork. And like, paperwork is a little bit more, there's more paperwork for foreign students. But yeah, no, there's a lot of, I mean, I work with a lot of foreign students.
Any more questions? All right, thank you very much. Student design team has a meeting here. Otherwise, I'll see you guys in 2 weeks. Don't forget to purchase your shirt. Support ACME.
Guys, with the stuff you presented on the website, that's stuff you learned in physics 3. So something to think about when you're thinking class.
I was thinking that.